language and behavior and attention. Methylmercury also can affect cardiovascular health in studies that have been done. I'm not going to talk very much about that, but it has been linked to increased heart attacks in men who consume fish. Those studies were done on men, so not women. I'm sure it may affect women as well. And so looking at this all has an impact on us and our society. It has economic impacts, it has societal impacts. And it's known that as you go above the reference dose of mercury in the blood, that IQ points decline. And it's also known that as IQ points decline, even small amounts of IQ points, that affects a person's ability to earn wages, to make a living, and that costs the U.S. annually hundreds of millions of dollars. The National Research Council estimates also that 60,000 children in the U.S. each year may require special education related only to methylmercury exposure in utero. And the cost of that education for those kids is close to $5 billion annually. And these are only economic costs. I think also about, what about the emotional costs to a family? What about the community costs? So it's not only dollars, but there are dollars that are involved here. In addition, currently, even today, there are too few child and adolescent psychiatrists to meet the needs of kids that have neuropsychiatric disorders. And again, I find this alarming because that is on the rise. So, almost done. All right, so what can we do about this? You know, as was said just a bit ago, okay, becoming aware, learning about this issue, recognizing, wow, we do need to do something. This is serious. And becoming engaged, talking to industry, talking to politicians, talking to agencies, and really working together to decrease emissions of pollution and lowering, in this case, methylmercury, but certainly other things as well. Make your voice heard. No one can do everything, but everyone can do something. And I would put forth that we must all be involved in reducing methylmercury exposure. Okay. Thank you.
Thank you, Dr. Nordine. We want to get a copy of that for everyone. And you were the guinea pig. In that, now we know that the table has to go. Okay. The next person that we're going to hear from is Dr. Eric Glass. Dr. Glass is someone who you may be familiar with. He grew up on Park Point, still lives there. He's been an active community member for as long as I can remember. What I didn't know until recently is that Dr. Glass has a PhD in chemistry. He had a National Aeronautics and Space Administration Fellowship, a NASA Fellowship. He's a rocket scientist. And was a scientist at the US EPA National Health and Environmental Effects Research Laboratory, where he was a senior research chemist. I had order of chemistry and it was really icky. Dr. Glass is going to explain to us what mercury is, what its forms are, and how it gets in our river, and why it's still in our river, and why it's in the fish we catch, and some thoughts about how to get it out. And he's going to do that in 9 minutes.
Next slide, please. This is all I know, so if you study this, then you'll have everything you need. Copies of my slides are on the back table with the SLSA group, so you don't need to take notes. You can get an actual copy of these things. What I've attempted to do here is to put into short form everything I've learned since 1985 when I started pursuing the topic of mercury. I was employed by the US EPA at the time, getting down from the acid rain program that I led for 5 years. Under the Reagan administration, they chopped my budget every year, so that was zero at 1985, so I had to find something useful to do under administration that was quite hostile to EPA employees, particularly ones that like to do things. And so I picked a topic that I know no one else would handle, one that had 5,000 lobbyists because there were 5,000 commercial products that used mercury at the time. So we've come a long way today to diminish the use of mercury in commercial products. And so you can actually buy a Ford car now without a mercury switch in it. So that's a great thing. So we've come a long way, and so what I wanted to quickly go through this, and I'm probably going to run out of time, so I'm going to again say the copies of my slides are in the back, so if I do run short, you can find this stuff there, and I will be happy to talk with you. When I started in 85, the US EPA detection limit was right at about the 10,000 mark. You could not see anything with official methods to the left side. Anything in the part per quadrillion was less than the detection limit. So EPA couldn't tell where the mercury was coming from in the fish. As ridiculous as that sounds, that was a fact. And so my first battle was to get EPA standard methods up to where they could do a part per billion. Sounds great. Then pretty soon, a part per trillion. And then pretty soon, 10 years later, a part per quadrillion. So we managed to push that through by hook or by crook with the help of the University of Minnesota at Duluth. I paired up with Dr. George Rapp, who was the dean of the Science and Engineering Department, both scientifically and politically. Whenever my papers were censored, I would get them published through Dr. Rapp and the University. So we had a dual joint partnership there. These are data that I actually measured at a monitoring stand, the data for air and for precipitation. And the reason for me dwelling on that is that mercury is everywhere. Mercury has been everywhere for all time. It is one of the elements, 92 stable elements in the periodic chart. The symbol Hg stands for, trivial question, anybody know what Hg stands for? No one? I win. Hydrogaurus, liquid silver. And if you look it up on Wikipedia, there's a really nice summary of methylmercury. So I'm not going to waste your time except to refer you to that. It was updated on August 25th of this year, so it's right with the hottest stuff right here. And so you will be able to see what this miraculous pollutant is doing and has always done, because it's always been there as a monatomic element that is liquid at room temperature. It has a vapor pressure at room temperature. That means it will evaporate into the air. And if you have mercury in your house, you will be breathing monatomic mercury. That monatomic mercury is a single atom of mercury that can dissolve in any fabric, any media. It goes places that no other element can go because it is a monatomic element. As soon as it makes up with something that wants to take a charge, it becomes a +2 ion. And that bumps into a methyl group on any kind of organic. You can transfer the methyl group onto the mercury. And you have a carbon-mercury bond form. And that's the methyl mercury that we all have grown to hate, because it does contaminate the food. Let me just say a couple more things that this shows the rough structure of the bioaccumulation layout. When you go from air to rainwater precipitation, that then goes and makes up the lake water or streams, runs into watersheds. Those watersheds and lakes generate zooplankton that bioaccumulate the plankton. And the red thing you see there is the methylated form of mercury. So a surprise to some will be that there is methylmercury in air, there is methylmercury in rain, and you don't need bacteria to have methylmercury. It can happen abiotically. In fact, I did that as part of my PhD thesis, to make metal compounds by stirring it up in water under general conditions. It's a very interesting reaction. And so it doesn't take high temperature reactions, it just is there. So if you have mercury around, you're going to have methyl mercury to the tune of 1 to 2%. And that's what we found in the rainwater that we've seen. And that 1 to 2% can itself be enough to give you some background level, even in the quadrant lakes, which we heard about here that we were worried about. Yes, we give that. Next slide, please. This is some of the air data we have for Duluth. I ran a station in a lot adjacent to my house so I could monitor it 24/7. And I did that for about 10 years. That monitoring station was built by the PCA, is now serving well on Park Point Beach as a pirate ship for my grandkids. The bottom curve shows the air concentrations that bob along at about 1 to 4 parts per quadrillion. And the peaks that you see are peaks that happen when you get a rainfall, because the mercury in the rain hits the surfaces, and some of it is mercury plus 2 gets reduced to Hg0 and adds to the background level. So that mercury gets cycled within the rain, some of it, as Hg0. Hg0 goes into plants, into the stomata. It gets absorbed. And when I was measuring the rainfall and focusing on what was happening in the air and in the rain, I happened to take a few of my maple leaves, and I was surprised to see several hundred parts per billion in the leaves themselves. So I know that the uptake is very significant just from Hg0 going into vegetation. Next slide, please. We set up monitoring sites across Minnesota and North Dakota and over into Michigan. And I sent out by UPS every week sample bottles that cooperators would take a sample, a weekly sample, and send it back to me. I drove the EPA nuts because I did all this on no budget. And so that was one of the amazing things that we could actually do a monitoring program across the state and across 3 states. Next slide, please. And get numbers that show the washout that's happening. This slide simply illustrates that the rain events wash the mercury out of the air. So the air is contaminated with mercury. Rainfall washes it out. The components of mercury that wash out most rapidly are the charged ionic forms. Hg0 does have a solubility in water, and some of that washes out. Then it rebounds back into the air. And the first droplets of rain are the most contaminated. The last droplets are the least contaminated. And this plot shows that relationship in terms of the rate of precipitation. And the other thing it shows is that there are significant differences between sites. And those significant differences show that the emission sources within the area do have a role and do contribute to the air concentrations and do contribute to the concentrations in the rain that washes out. Next slide, please. The whole focus of this is to figure out why and where it was coming from to get into the fish. Always the fish has been the focus, and to understand why how this element that has been with us forever since the beginning of time does bioaccumulate. This is a lab study that I did in the late 90s, published in 2001. An abstract on the back table describing the findings. And I point this out. First of all, we did 80 lake study, and then we did a subset, 20 lakes, that we could do a more in-depth study on methyl mercury and the bioaccumulation factor of methyl mercury itself. And so I wanted to indicate that these are 20 lakes, and the red line around Lake Superior is something I want to point out to each and every one of you. Like me, you all grown up learning that the outline of Minnesota looked like it did in black, when in fact there is a boundary in Lake Superior showing that we have several million acres of Lake Superior, part of the Minnesota official boundary. And so Minnesota should always have that red area outlined, and we own that part of Lake Superior. So I want you to realize that and correct the next map that comes up, and you have the opportunity to correct including the USGS, state of Minnesota. Everybody that uses that, they ought to have the official area that Minnesota is and should be responsible for. I made that statement to a representative once that, geez, now your district contains Lake County, the old part of Lake Superior. She looked at me like I was crazy, but maybe I am. This does, in fact, show the legal boundaries of the lake, and I think that also is one of the lakes that we want to focus on as part of this. Next slide, please. I will show you a little bit about the fish data. When we did our first studies, we did things in terms of standard fish size, because it's hard to catch the same size fish from every lake if that's what you want to do. And it's also hard to catch the same species of fish from every lake if that's what you like to do. So what biologists do, they set their nets and they take what they get, and then they do the calibration and they say, well, we're gonna compare these lakes by taking the same fish size and the same fish weight. And we did the same thing. Well, we found out that there was a lot of scatter in the data. Didn't make a whole lot of sense in some respects. So here's what we did a third time around. We took the age of the fish. And we found out that, the fish showed a much better relationship statistically by taking the mercury concentration with age as it did between mercury and length or mercury and weight. And all of these lakes, anything above, let's take the weight on top. The 1,000 mark on the top would be 1 kilogram. Anything between 1 kilogram and this way to the 200 mark would be edible 1 meal a week. Anything above that, only 1 meal a week to 1 meal a month, one or none. Tooth Lake is my favorite. It's favorite because it's so high it's out of sight. Next slide, please. Again, this data is on the back, and you can pick up a copy at your leisure. This is a relationship that shows the weight and length relationship, how if you catch a fish of a given length, you pretty well know what its weight is, or if you catch a fish of a given weight, you know what its length is. But that doesn't tell you what its age is. And the really interesting thing is, you can have a fish that's 40 centimeters long, that's something more than 30 inches, and it can weigh anywhere from a small amount to a large amount depending upon what the age is. In other words, if you catch a fish of 1 kilogram size, it can be 2 years old in California, or it can be 7 years old in tooth. And the amount of mercury in that fish is exponential. It goes up as an age squared. So you want to eat the small fish always. You don't want to eat the big fish. Time is up. No problem. Last slide. Last slide. Last slide. One more. Last slide is a list of papers you can also get out at your request.
Next, we're going to hear from Len Anderson. Len has a master's degree in aquatic and terrestrial ecology from St. Mary's University. He has spent 45 years studying the ecology of the St. Louis River watershed, worked to protect it, and teach others to protect it. Len's going to share with us the history of our community and state and national efforts to remove mercury from the St. Louis River, as well as his suggestions for the future. Welcome, Len.
Thank you, Kristen, and thank all of you for taking the time to be here this evening. We really appreciate your attention and the fact that you come here, and hopefully we can pass on some information that will be beneficial to you. I'm an old retired teacher, and I know that for many of you, a couple of the classes that were the most boring and the ones that you wanted to get out of would have been your history class, maybe your science class. So what's my assignment? Talk a little bit about the history of this mercury issue in our area and a little about the science of it. Let's start with the history first. There will be a final exam. That's the bad news, so I'll get to that at the very end. But let's start with the history. And it goes back to 1998. We had a meeting down in the Radisson here in Duluth on the topic of fish tissue mercury in the St. Louis River watershed. And we had a group just like this, people that really were honestly concerned about it. At the end of the program, we had a sign-up sheet that was available for people to sign up if they were willing to commit themselves to try to make a difference and help get the mercury out of our fish. 250 people signed up. That was very encouraging. Well, after a few years, that evolved. Some of the people, in fact, I see quite a few faces out here that stuck with it and ended up on a St. Louis River Mercury TMDL partnership. And we worked for 7 years. We learned a lot about mercury. We learned a lot about politics. And at the end of 7 years, we'd gotten to the point where we thought we had a pretty good handle on what it would take to get the mercury out of our fish. We were starting to understand the science a little bit, maybe not to the level that Gary does, but we were starting to get a handle on it. And we were looking at a model that would tell us just what kind of an allotment would we need to clean up this river. That's a TMDL. The state, I think probably correctly, told us that this model was not good enough. And the main reason it was not adequate was that it did not deal with the issue of sulfate. We had good models about all kinds of other things that are going on in any watershed, but we did not have that one component at that time. And I think without that, the model should have been rejected. At about that time, the state of Minnesota embarked on a huge project, and that is to put together one giant TMDL for the whole state. And that was a mercury TMDL. And it was a difficult process. I think it was a good process. We won't know for a few years if it's going to all work out, but I think it was done well. MPCA showed great leadership. And we now have, the implementation of that TMDL is going on today. And hopefully most of the lakes and rivers in the state will produce fish that are edible for everybody in the near future as a result of that. However, unfortunately, we were told that our river wasn't going to make the grade, and that we were not going to be able to eat the fish out of our river by the year 2025. Very disappointing. We passed on the information at that time that we thought that there were some unique characteristics of our river that had to be looked at if we were ever going to be delisted. We know that we live in a part of the world that is sulfate poor. The numbers going back into the 1940s show numbers like 3 or 4 milligrams per liter for the tributaries that come into the St. Louis River. That's very low. We have now become a sulfate-rich water body. Unfortunately, there are times when we're looking at flood stage when we are delivering 200 tons of sulfate to this watershed every day. That is a massive amount of a very dangerous chemical. Now, you could drink that water, it wouldn't hurt you, but we'll try to show you in a couple of slides here what the problem is with all of that sulfate rushing through our various wetlands and through this entire watershed. First slide, we're talking about low oxygen aquatic systems. And that means that sometimes during the hottest day of the summer, when things are drying up, there's really no oxygen in those sediments. That marsh just doesn't have any oxygen in the sediments. The estuary has a lot of water like that. Beaver dams, floodplains. So it's going to be some of the ecosystems that are common in the St. Louis River watershed will be low oxygen. Next slide, please. These are the players, as I say, that have to be involved for methylation, for most of the methylation to occur. There's some other minor players, but these are the major players. You have to have mercury. We're not going to cure China and India of their mercury habit. They're going to burn coal for a long time. It becomes a part of the global dispersion of mercury, and we're going to get a lot of their mercury. And it, as Gary was explaining, falls out of the atmosphere, it's washed out of the atmosphere, and it's going to be there for a long time. It's an element, it won't be destroyed. It also has to take place in carbon-rich sediment. You ever jump out of your canoe and you're paddling the St. Louis River, you know that, well, if you're barefoot, you know that that black ooze that comes up is carbon-rich. All of our wetlands are. They're carbon-rich. So we can't do anything really to correct what's coming from the global airshed. We can't